यहाँ पे start कर ले मैम.
So today we'll be doing statistical quality control. What is statistical quality control? Statistical quality control, or as usually it is known as SQC, is the term used to describe the set of statistical tools used by quality professionals to improve the quality of any manufacturing product. We use statistical techniques, and this is known as statistical quality control. So what is the history? SQC was pioneered by Walter A. Stewart at Bell Laboratories in the early 1920s. So most of the revolutions which have been brought up in the management field, generally it has come through Bell Laboratories, and this is one of them. Stewart developed the control chart in 1924 and the concept of a state of statistical quality control. Somewhat consulted with Claude Simon in the application of control charts to munitions manufactured at the Army Arsenal in 1934. So along with Stewart, there's another gentleman, Simon. Simon also, like in decision making, also we take his guidance. Both of them used this in the Army Arsenal department in the manufacture of munitions. Then came Deming. Deming is usually we associate his name with quality. Like even a award is given in this sector by his name. W. Edwards Deming invited Stewart to speak at the graduate school of the U.S. Department of Agriculture and served as the editor of Stewart's book Statistical Method from the Viewpoint of Quality Control in 1939, which was the result of that lecture. Again, it's not it's quite some time back when these things have been started. In 1939, Stewart delivered his lecture at the request of Deming. Deming was an important architect of the quality control courses that trained American industry in the new textiles during World War II. So during World War II, because of these techniques, the Allied fields were able to win the war. Deming traveled to Japan. Deming has done a lot of work in Japan. In fact, he was more appreciated in Japan than in US. Even though he was from US, but he has worked for a number of years in Japan, and that is the time when Japanese goods improved immensely in terms of quality. Like in 1950s, it was known as Japani Mal. Japani Mal is of very mean quality, of no quality. But because of Deming's involvement in quality control, this changed. And now when we are talking about quality, Japan comes first in our mind, even before US. Deming traveled to Japan during the Allied occupation and met with the Union of Japanese Scientists and Engineers, JUSE, in an effort to introduce SQC methods to Japanese industry. So we use three categories in this SQC. First is your descriptive statistics. Second is your statistical process control. And third is your acceptance sampling. Now, what is descriptive statistics? That is usually the statistics we start learning right from our childhood. Like in your school, we are taught mean, median, mode, what is. So it describes a population or a sample. Like generally in statistics, what we do is we don't take the whole population because sometimes it is very difficult, it might be very costly, and it is not worthwhile. For example, if you want to study some chemical, so we cannot use the total chemical because the chemical will be destroyed during that study. So we take a sample from it. So sample should be, as far as possible, it should be a true representative of the population. We should take, there are many ways of calculating sample or selecting sample, and so that whatever inferences, we draw inferences from the sample about the population. So we should be very careful how we select the sample. So descriptive statistics is about the sample mean or median or mode, whatever central tendency. That is the central value around which all the other values lie. And standard deviation, the deviation or the variation in the statistics. Just generally, if you don't go it very mathematically, also we can say that if the population is homogeneous, very small sample size can also tell you the condition of the population. For example, suppose if you are cooking rice, even if you are cooking in a small vessel or a very big vessel, you take out only one rice and you can make out it is cooked or not. So it does not mean that every time the sample size should be large. It depends on the variability in the population. If the variability is large, then the sample size automatically will be large. So any inferences which we make, it is for the population. The first is the descriptive statistics are used to describe quality characteristics and relationship. In that, the mean is the measure of central tendency. Generally, we take arithmetic mean, but sometimes we can take, as the situation lies, we can take median or mode also. But generally, in statistical quality control, we are talking about manufacturing units, and there we take mean, measure of, this is a measure of central tendency. Then we take range. That is the difference between the smallest and the largest. Suppose the height, if you are taking, I'm just giving an example, it is not from manufacturing unit, but suppose we are taking measurement of 100 people, the height of 100 people. There must be one least one, or it can be more than one also, but there will be one least value and one largest value. The difference between these two, this is known as the range. Standard deviation is measures the amount of data dispersion around the mean. Around the mean, how the other data are deviating. That is also a measure of dispersion or variability. How do we calculate mean? Mean is nothing but you sum up all the observation and divide it by the total number. X bar, which is the mean, is equal to sigma xi. I is equal from 1 to n divided by n, where x bar is the mean, xi is the observation, number of observation from 1 to n, and n is the number of observations. Suppose if you want to find out the average numbers which you have received in your class, so you add up all the subjects number and then divide it by the total number. And what is range? Range is the difference between the highest value, which over here it is 9, and the smallest value is 3. The range is 9 minus 3 is equal to 6. And this is standard deviation. Standard deviation is a measure of dispersion of a curve. So it is nothing but xi minus x bar, because it is around mean. X bar is nothing but mean. So how it is deviating from the mean. So x minus x bar whole square, you sum it up and divide it by n minus 1. Over generally, if you are taking the population, it will be n only. But since we are taking sample, so 1 degree of freedom is lost, and that is why it is n minus 1. This is variation. And square root of that is standard deviation. Standard deviation is nothing but the square root of variation. Sigma denotes standard deviation, x bar the mean, xi the observations, and n is the total number of observations. Standard deviation is a measure of dispersion of a curve. It measures the extent to which these values are scattered around the central value. Each value. Then next is your statistical process control. So we use this descriptive statistics to study statistical process control. How we will use this statistics to control the process of manufacturing. Extend the use of descriptive statistics to monitor the quality of the product and process. Statistical process control help to determine the amount of variation, because like we cannot have, like suppose if we are manufacturing, say uh, we are manufacturing, say a bag of cement, which mean is 40 kg, but each bag will not be exactly 40 kg. Some will be little bit more than 40, some will be little bit less than. So how much variation should be allowed? That is not possible to have each and everything having the same mean, because we want it to, we sell it also in the market as 40 kg bag, but every bag will not be exactly 40. But the variation which is allowed, that is the mean. That is what we want. So we should also know the standard deviation, how much it should deviate from the mean, and how much it, like go up from the mean or down from the mean, to make sure the process is in state of control. So by controlling this deviation, we can say whether the process is under control or not. Variation in quality. Quality. No two items are exactly alike. That is what I was saying. If you are manufacturing bag of 40 kg cement, every cement will not be exactly 40 kg. Some will be less than 40, some will be more than 40. Some sort of variation in the two items is bound to be there. In fact, it is an integral part of any manufacturing process. So you cannot have exact. So you have, so what should be that variation? How much it should be allowed, and which should be acceptable by the market, by the consumer, and also by the manufacturer. The difference in characteristics known as variation. This difference from the mean is known as variation. This variation may be due to substantial quality of raw material, carelessness on the part of operator, fault in machinery system, etc., etc. There can be number of causes. So there are basically two types of variation. One is variation due to chance causes and variation due to assignable causes. Variation due to chance causes, or we can say common causes. Variation occurred due to some chance. This variation is not due to defect in machines, raw material, or any other factors. Behave in a random manner. There is no set pattern. Negligible but inevitable. It is random. It will always happen, no matter how minutely, how genuinely you have set up the whole process. But something or other might happen, and the variation will come into picture. the process is said to be under state of statistical control. But this small variation is allowed and it is accepted. And we can say the whole process is under statistical quality control. Now, variation to assignment because of something which we know why it has happened. Variation due to assignable causes, that is non-random causes like difference in quality of raw material. Because of the raw material, some difference will happen. Difference in machines, difference in operators, differences of time. So because of this, we have assigned it to raw material. We have assigned this cause due to machine, the type of machine which you are using, or the person who is operating the whole operation, or because of time, things, this will happen. So if it is under control, so generally we say that the distribution follows a normal distribution. This is a normal distribution where the mean, the median, and the mode are the same. Here, mean is equal to mode is equal to median, and 50% is lies between mean and 50% lies above mean. And actually, it does not touch the x-axis. It touches x-axis at minus infinity and plus infinity. At infinity, that means asymptotically it touches. So what happens? We say from this is the mean. Now if we add plus sigma, 1 sigma, and minus 1 sigma, the area in this region plus minus 1 sigma is about 68%. Plus minus 2 sigma, it is about 95%. And plus minus 3 sigma, it is about 99.7%. So almost, this is not 100%. 100% will come between minus infinity to plus infinity. That we cannot control. So we can control till 9. If the your whatever variation is there is lies between these two from plus minus 3 sigma, we say it is normal cause and we accept it. And if it is some assignable cause, it will be beyond these two lines. This is known as the upper limit and this is known as the lower limit. No item in the world can be a true copy of another item. With mechanization and automation and computerization, we are mass producing. Even then, very, very slight differences can be there in the things which are being manufactured. It is not expressed in absolute values, but in terms of range. So this is the range, not absolute range. Thoda zyada, thoda kam, it will be there. For example, the diameter of a pen is expected by its manufacturer, not as suppose the diameter, I say it is 70 millimeter, but it is not 70 exactly. All the pens will not be exactly 70 meter. It will lie between range plus minus 0.05. So some will be highest if I take it is 7 plus 0.05 and the least I can take is 7 minus 0.05. Others will lie in between these two values. Thus, the diameter of a pen produced by the manufacturer can vary from 6.95 millimeter to 7.05 millimeter. Plus minus, this is minus, and this is plus. As I told you, this I'm just repeating this. This is the mean in the middle. 50% is above mean and 50% is lower mean, and plus minus 1 sigma, that is 1 standard deviation, 68% lies. Plus minus 2 sigma, here it is written as 1 sigma, plus here it is minus. About 95% lies between it, and about 99.75% lies between plus minus 3 sigma. And the upper control limit is at plus 3 sigma, and lower control limit is at minus 3 sigma. This is UCL, upper control limit, and this is LCL, lower control limit. This can be one example. Suppose something we say ki mean is 16 millimeter, or it can be meter or whatever. It is one, I've just taken one value, 16. And the variation I've taken as plus minus 3 sigma as 16.2 and 15.8. Plus minus 0.2. So it lies, the variation is between 15.8 to 16.2. And if the value, whatever I'm manufacturing, it is, I've taken how many observations? 1, 2, 3, 4, 5, 6. So 5, 6. The first 5 is within that control limit. So either I can accept this, or I can, because only one is out, and that is also not very much out. It is somewhere in it, 16.2 ke pass, it's somewhere near it. So I can accept this sample. The control charts are what? They are graphs which are plotted on a chart where at the middle is the control limit, and upper limit is the upper control limit, and the lower limit is the lower control limit. Control charts for variables, and we have control charts for attributes. Variables are used to monitor characteristics that can be measured. Example, length, weight, diameter, time. We can measure this. But attribute means it can be said whether it is present or it is not present. Control charts for attributes are used to monitor characteristics that have discrete values that can be counted. It can be counted, that can be measured. Variables can be measured, an attribute can be counted, or it can be present or not present, or if it is present, in how many numbers it is present. Suppose we are seeing the control of a cloth, whether it has got some spot on it. So say we take a sample of say 5 by 5 meter of a cloth and see how many spots are there in that cloth. So it can be 1, it can be 2, it can be anything, n. So it is a attribute. It is not a variable. It is an attribute. It is present or it is not present. Control, and how many of it is present, that will be its number. Control charts for attributes are used to monitor characteristics that have discrete values and can be counted. Example, defective number of flaws in a shirt, number of broken eggs in a box, something like that. So it is countable and this is measurable. Now we are going to learn how to constructing a X bar charts. Here sigma is not given. Sigma is what? Standard deviations. You don't know the standard deviation. So we can make use of this chart, control charts, to find out. Now, the problem is a factory produces 50 cylinders per hour. Samples of 10 cylinders are taken at random from the production at every hour, and the diameters of cylinders are measured. Draw X bar and R charts and decide whether the process is under control or not. So first of all, let us find out X bar and R bar. X bar is nothing but sigma X divided by M, and R bar is nothing but sigma R, which is equal to summation R divided by M. Actually, we have taken 10 samples. So here it is sigma bar. of each sample and then finding the grand mean of that. This is the data. See, we have 4 samples, X1, X2, X3, X4. Each sample has 10 units. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the measurement is given over here. 230, 238, 242, and so on and so forth. So first of all, you find out the mean of each sample. It is 960 over here. The mean is this 960 divided by 4. And range is the difference between the highest is 250 and least is 230. The difference between these two, so that is coming to R. So for each sample, we find out the mean and as well as the range. So for each sample, there are 10 samples and each sample has 4 units. So here the mean is 240, 227.50, 232.5, and so on. So the total of mean is 2345 or 2345.75. And similarly, I have found out the range for each sample. So between the highest and the lowest. The first is 20, second is 24, third is 18, and so on. And we have found out the summation, 196. Isn't it? So from this chart, we can find out the grand mean. Grand mean is X bar, summation X bar divided by M, the number of samples. So here, sorry, this is 2345 divided by 75. So this is 2345.75 divided by sample size is 10 divided by 10. So if you divide this by 10, it will be 234.75. Actually, it is 0.57. It will be. It's nearly equal to 0.75. And similarly, we have found out the range, summation of range, 196 divided by 10. So it is coming to 19.6. So once we have found out, and this is my control chart. Just like you have standard deviation chart, you have control charts. So here, these are the sample size. For X bar, A2 is given, and for R chart, D3 and D4 are given. So our sample is 10, so we will take 0.31. So this is my control limit, X for X bar. And first I'll do for X bar. It is nothing but control limit at X bar, X double bar. And we have calculated X double bar as 234.75. So this is my control limit, the middle line. Then upper control limit is X double bar plus A2 into R bar. A2 is from this chart. A2 when 0.31. Oh, sorry. It has every sample has 4 units. So it will take at 4.73. And R bar we know is 196. So upper control limit is coming at 249.06. Similarly, this is same as lower. It is because it is symmetric in nature. I said plus minus 3 standard deviation. Here, our standard deviation is not taken into account, is not given. When standard deviation is not given, then we take range, because range is also a measure of variation, and the control charts, value from the control charts. And lower control limit will be x bar minus A2 into R bar. So that is coming to 220.72. So when we draw, see, this is our diagram. This is 230, we can take as 235 almost. So this is our control limit 235. And then for I have got 10 samples. Each sample is of 4 units. So from each bar I'll take 240 to 27.50 and so on, 10 values. And I'll plot this over here. So you see, all are lying between plus minus 3 sigma. UCL, between UCL and LCL. All the values, no value. It is slightly up, but it is only very slightly above UCL. So we can say that this sample is acceptable. It is under control, statistical quality control. Similarly, we can find out the R bar. That was for X, mean. Now this is for range. So again, here central line is R bar. That was coming to 19.6. Then upper control limit is DR by R bar. So we know DR from this. When 4, DR is 2.28. into 19.96. So it is coming to 45.50. And similarly, if I find it is D3 by R bar, so it is 0 over there in the control chart. D3 is 0. So we have found out the value for upper control limit and lower control limit. Mean should be 19, the range. The mean should be 19.6 and the upper limit for the range is 45.50 and for the lower limit it is 0. If we draw this, we get, so it is also under control. In the range region also it is under control. It is lying between UCL and LCL. That was when we did not know the sigma, but we knew the range. So we use control chart. When we know don't know the sigma, but we know the range and we use control chart. But when we know that sigma, that is the standard deviation, then we don't need that. This is another example. A quality control inspector at the Coca-Cola soft drink company has taken 25 samples with 4 observations. Each of the volume of the bottles filled. The data and the computed means are in the next table. If the standard deviation of the bottle operation is 0.14 ounces, use this information to develop control limits of 3 standard deviation for the bottling operation. So here we know the sigma. So sigma we take plus minus 3 standard deviation. So this is the We have total 25 samples. Each has got 4 observations. So for average, for every sample, we take out the average, and then the total average is 39.87. Similarly, we take out the range for each sample. There are 4 observations. We take out the range and then find out the total range. Here we don't need control chart. Here, if you are finding out for the mean, X double bar will be what? The total observations of X bar divided by the, you have 25 observations, so divided by 25, which is coming to 15.95. And the standard deviation plus Z6, because we are taking Z over here is 3. I told you the plus minus 3 sigma, about 99.7% lies between this. So we take Z as 3. And we know it is standard deviation was given as 0.14. That was given in our problem. This is the formula. UCL is X double bar plus Z sigma X bar. And LCL is X double bar minus Z sigma X bar. So you're using this formula. So it is, we know that F, that is from the sample. The sigma, that is for population, and small s is for sigma of sample. So here S is 0.14 divided by under root 4, because it is under root n. N is what? N over here is 25 divided by, actually it should be 5 over here. So from here we found out the value of upper control limit and lower control limit. And then we draw the graph, plot the graph. We get everything is between upper control limit and lower control. For each sample, the mean of each sample. And we see it is between these. So this process is under control. The mean is under control. That was for variable. Mean is for variable, where we can measure the difference, like length, diameter, all these things. And P chart is for attribute, whether it is present or not present. If it is present, then how many of it are present? Some defects. A production manager of a BKT tire company has inspected the number of defective tires in 5 random samples with 20 tires in each sample. The table below shows the number of defective tires in each sample of 20 tires. Calculate the control limits. So we have 20 sample number of how many were defective. In the first, there were 3 defective. Number of observations out of 20, 3 were defective. So out of 20, so fraction defective will be 3 divided by 20. So here we find fraction defective, because each number of observations in each sample was 20. It has been rounded off. So we find out the total number of defective tires and the total number of observations. So here the formula changes a bit. Control limit is P bar, total number of defective tires divided now by total number of observations. So from here we have seen total number of defective is 40 and total number of observation is 400. So P bar will be 40 divided by 400. So it is coming to 0.10. And sigma, that is the standard deviation, is calculated as under root P bar into 1 minus P bar divided by N. So we know P bar is 0.10. So 1 minus P or 1 minus, that is 0.90 divided by 20 and take the square root of that. So that is coming to 0.067. So this is my control limit, 0.067. So you can see this is my control limit, 0.067. And this is P bar plus Z P sigma P. And lower will be P bar minus Z. Z we know plus minus 3. So it is here 3. Here it is 0.067. Here again P bar we have calculated is 0.067. So we get upper control limit as 0.301 and lower is minus 0.101. When it is minus, nothing can be, attribute cannot be minus. So that is why this is taken as 0. So here is the graph. You have 20. So you take all these and see whether the range is within control limit or not. So over here we see it is within control. Nothing is beyond UCL or LCL. The number of defectives. Here it is another. Here we are using chart. The number of weekly customer complaints are monitored on a large hotel using a C chart. Develop 3 sigma control limits using the data table below. Again, here, first week, second week, till 20 weeks, we have seen the number of complaints in a restaurant. In first week, there were 3 complaints. In second week, there were 2. Third week, 3 complaints, and so on. So again, we find out the average number of per week. So that will be how much? 20 weeks were there and total was 44. So 2.2. So control, the central limit is 2.2. And in that, plus Z is 3 and square root of C. So we take 6.65 and another is coming as minus. So we get as 0. So again, you take this is 6.65 and this is 0. And we see the if you of the all the 20 weeks, you see it is under control. Nothing has gone beyond that. If the complaint had gone beyond that, then naturally that means the process was not under control. What is process capability? Evaluating the ability of a production process to meet or exceed preset specification. This is called process capability. Like I have set a specification. My product diameter or height or weight or number of defects, whatever it is, should be this. Whether I'm meeting that criteria or not, that is process capability. Product specification, often called tolerance, are preset ranges of acceptable quality characteristics such as a product dimensions. There are two parts of process capability: measure the variability of the output of a process and compare that variability with a proposed specification of product tolerance. Actually, see, the difference between UCL and LCL is what? Plus and minus 3. So together, it is not being added. Plus 3 and minus 3, if you add, it will become 0. But you are taking the whole distance from minus 3 to plus 3. So that is 3 sigma. To produce an acceptable product, the process must be capable and in control before production begins. So this is my process capability. That is the difference between upper control limit and the lower control limit divided by 3 sigma. Let's say that the specification for the acceptable volume of liquid is preset at 16 ounces plus minus 0.2 ounces. This is my accepted. Like, even I'm accepting that there will be variation, but that the variation should be between plus minus 0.2. That it should be between 15.8 to 16.2 ounces. If CP is 1, then that means LCL. The difference between LCL and 3 sigma is same. It is the difference between LCL and UCL is 6 sigma only. So 99.74% of the product that volume between 58.8 to 16.2 ounces. If CP is less than equal to 1, so we have already seen, so it is less than 1. The process produces 99.74% 3 sigma of the product between 50. अब यहाँ क्या हो गया उसे 15.8 से it is coming down and it is also going up. Or if just the reverse of that, CP is more than 1, then it is 16 is the control limit and 15.8 was the lower control limit and 16.2 was the highest control limit. So this is less than that. So actually it's less than that. It is 15.9 to 16.1 ounces. One means UCL and it is in between the specified control limit. It is less than that if it is more than 1. If it is more than 1 again, it is 1.33 and this is 1. So it is a higher quantity than that. That is why it is a more peaked diagram. And here it is again more peaked because it is 2. Suppose you have a bottling machine at Coca Fizz are being evaluated for the capability. The bottling machine A, B, and C. Standard deviation of A is 0.05, standard deviation of B is 0.1, and standard deviation of C is 0.2. In specification are set between 15.8 and 16.2. Determine which of the machine are capable of producing within specification. So you know the 15.8 to 16.2. That is my control limits. UCL is 16.2 and LCL is 15.8. So the difference is 0.4. So if it is machine A, then the standard deviation is 0.05. If it is machine B, it is 0.1. If it is machine 2, C, it is 0.2. So I divide UCL minus, that is 0.4, 0.4, 0.4 by, first by 0.05, second by 0.1, third by 0.2. And I get this value. So this is what CP is more than 1. These are less than 1. So we reject this and only accept A. One तक कर सकते हैं, more than 1 we can accept, but not less than. ताकि जो preset limit है, either it can be till that or more than that. Then what is process capability ratio? There is a possibility that the process may shift over a period of time. It is dynamic. It can shift over time period in either direction, that is toward UCL or LCL. This may result in more defective items than the expected. This shift of the process mean is called the off-centering of the process. So we take the minimum of from UCL to mean. Up till that is only 3 sigma, and from mean to LCL, that is again 3 sigma, half. So mean of these two things. Now, for example, your mean is 15.9. Process standard deviation is 0.067. LCS is just like in the last example, 15.8 and UCL is 16.2. So CP is what? CP will be LCL minus, UCL minus LCL divided by 6 sigma. Sigma is 0.067. It is 0.4 divided by this number, 6 into 0.067, which is coming to 1. Now PK, the minimum of these two. Again, we put up the same value. 15.9 was the mean. 16.2 minus 15.9 divided by 3 sigma. Similarly, 15.9 till from mean to the lower limit divided by 3 sigma. So this is coming to, the mean of this is 0.33. So we can take up till 0.33. We have can do that. So that is all for today. Thank you very much.